topic, which is inner product spaces. So in the previous lecture, we discussed the convergence of a sequence in metric space, and we discussed some examples that whenever a sequence basically, so that is a sequence of functions from natural number to complex number or real number, converges to another sequence, that is basically in L1. So with respect to D1 now. So that is exactly this condition. And whenever this happens, then for every j, xnj converges to xj as a real or complex number. Right? Depending on whether we are taking real sequence with real entry or complex entry. Similarly, in L2, the sequence xn converges to sequence x. That means we are using second metric, D2 metric, and there we have a square here. And whenever this converges, again xnj converges to xj coordinate wise, right? For each j, it converges as a real or complex number. And similarly, third yes, we are taking xn, which is a sequence of real or complex number, which converges to sequence x in L infinity. So L infinity means we will consider the infinity metric, and D infinity, it converges means by definition it satisfies this property, and this property is satisfied. That means for every j, xnj converges to xj as a real number or complex number. So basically entry wise, so this condition is basically known as entry wise or component wise convergence. So whenever it converges in supremum, it converges entry wise. And then we have discussed one example of a particular sequence is En, whose nth coordinate is 1, other coordinate is 0. So those sequences can be considered as a function like Dirac, in the Dirac notation, right? So basically this is delta nj, and so enj is delta nj, and it converges to 0 as n approaches to infinity for every j. So basically what we are saying here is that the jth coordinate converges to 0 as n tends to infinity. Yeah, so coordinate wise it converges to 0, but if you form a sequence which has all entries 0, then En sequence converges to 0 sequence does not converge to 0 in sequence in one distance, right? Because d1 of En and 0 sequence is exactly this quantity, which is 1, right? And this is 1 for every n. For all natural number. D1 of En, distance of En with 0 sequence is 1 for every n, and then we take n tends to infinity, so that is basically the constant sequence 1. So this converges to 1 actually as n tends to infinity. So what we are saying is it doesn't converge to 0, but here it is converging to 0. For each j, it converges to 0, but as a sequence of sequence, it doesn't converge to 0 sequence in either of the metric. Fine. So after that, we started metric spaces in which we discussed closed sets. So closed set can be defined using the convergence of a sequence. If every point is a limit point, every limit point belongs to the set, then it is closed. And then we define the closure of a set. So whenever the closure of the set is the same set, that means it is a closed set. So once we know closed set, we can define open set, and then we define special open set. So this basically this is a neighborhood. Right? And in terms of topology, these are the basic open sets, right? Like intervals. Here we have a open balls, open disk in R2. If X is R2, this is the open disk. Yeah, so that is we discuss here. So if we take X equals to R2 and we define the open unit disk center at origin. So this is origin. This is not 0, right? This is origin 0, comma 0, and this is the radius. 1 is the radius. So with respect to Euclidean norm, if we define this set, then that is exactly the this is interior of the unit circle. So that is actually known as unit disk, open unit disk. Centered at origin. Right, but if we change the metric, then over the same set, if we consider one metric, then that is not the open unit disk. Instead of that, we get the diamond shape. The point, all points in this set are actually all these points. And the same way, if we take the maximum distance, then the elements of this open ball with respect to d infinity metric are all these points. Yeah, so how it is coming? Because if maximum is less than 1, then modulus of y1 is also less than 1 and modulus of y2 is also less than 1. And converse is also true. Modulus of y1 less than 1 and modulus y2 less than 1. Then maximum of that is also less than 1. So therefore we are getting this set using this condition. Okay, so the subset P of X is open if every point is an interior point, right? So interior point means in the metric space, it means around every point we can find the open unit ball. So open ball. So center at that point and radius is positive. For every x, there exists argument 0 so that this condition is satisfied. We can find the ball entirely contained in the set, then that set is open set. Right, so if we use this as a definition of open set, then that will give us our open set is basically union of UXR. So this is a basis. If you consider topology, this is a basis, right? If you take the set of real numbers, then this is nothing but the neighborhood. So neighborhood means it is an interval. So union of all intervals is open sets, all open sets in R2. Similarly, if we take R2, then these neighborhoods are nothing but the open disk. So every open disk, every open set in R2 is a union of open disk. Alright, so that way we can go for the several examples of topological spaces. In general, if I have if we have a matrix space and any subset of matrix space is open if E is a union of the open balls. Yeah, so there are some examples. Let us see. So we'll come back to these. So these are the properties of this is basically the definition of topology. The subset is dense if its closure is X. So that you know. And we discuss separability and co-sequence, bounded sequence. All these things we know already. Let us keep this quickly. So complete matrix space is the matrix space in which every co-sequence is convergent. So we'll see that these spaces are complete. And yeah, so we define the nonlinear space, and there is a relation between norm and the length. So if we have any vector, then the length of the vector is basically its distance from 0 to that vector, right? So that is exactly this thing. So norm of x is basically distance of x with 0, but this is true for only for the vector spaces, right? Otherwise we cannot use this. Okay, so we define the norm which is coming from the matrix in the case of L1, L2 and L infinity. So L1, L2 and L infinity are non-linear spaces, and yeah, so this matrix is very interesting. So if you want to find what is the topology, what is the topology generated by the trivial matrix, and for that we need to find what are the basis elements, right? So basically we need to find all these sets UXR with respect to the trivial matrix. If we take any non-empty set and if we define the basic open set, then what are the basic open sets here? Basic open set is basically y, so that distance of x with y is less than r. So we know that distance is either 0 or 1. So if suppose we take r is less than 1, r is anyway positive. So if we take r is less than 1, then what will be dxr?
Singleton X.
That will be singleton, right? Because if x with y we take different from x, then the distance is 1, but we are taking only points, so that distance is less than r and r is less than 1. So that means we are taking this to be singleton x. Yeah. So just a minute. I'm in lecture. 5:30 I will call you. Yes, so just I got some call from Dr. Sunil. So this is singleton. You are correct. And what about if we take r is greater than equals to 1?
Whole space X.
That will be the whole space x, right? Because there are only either we have x point or all other point has distance 1. So these are the two possibilities. Open sets. So in other words, what are the basic open sets? They are either singletons, right? Because this we get for every x and the whole set. So basic open sets are either X or singleton X, where X is an element of X. So all open sets are so what are the open sets? Open sets is basically the union of basic sets. So why did we mention that? Yeah, so if you want to find all open sets, then open sets are basically the union of UXR. And UXR are either this set or this set. So depending on which set we are taking, we will get the all open sets. So what are the open sets? That are unions of basic open sets. So this union we can select finitely many element also, infinitely many elements also, right? So depending on that. So in particular, all singletons finite sets of X are open. Your finite set we can write as a union of singletons. Right. So in short, all the subsets of X, right, are open. Because if you take any subset A of X, then we can write A as union of singleton X, X belongs to A. And each singleton is open, so union of that is open, so A is open. So if we take this simple metric, or it's a discrete yeah, so simple metric, trivial metric on an unempty set, then in that metric space, all the subsets of X are open. So a topological space in which all the subsets are open, that is called the discrete topological space. So this topology is coming from the metric. It is a metric space, and we have identified what are the open sets. So therefore it is a topological space. Okay, so that is just an example with the matrix space. Okay, so today we want to discuss inner product spaces. So let us start quickly with the definition. We already know the definition. So here we are discussing real and complex inner product space in a combined way. So inner product on a vector space which is real or complex is defined as the function which is a v cross v2 c, which we defined by the first property is xx is non-negative, right, and xx is 0 if and only if x is 0 vector. Second property is xy is equals to by x conjugate, right? So basically we are considering v over v is a real or complex vector space. So if you take real, then this is in a product xy, box x y is box y x, but if we take complex vector space, we need to take conjugate here. So this is complex conjugation, and The third property is linearity. So linearity we are taking in first variable. The second property will imply linearity in conjugate linearity in the second variable. So here I have not written, but basically x, y, z are elements of x and k is element of k, where k is either set of real number or complex number. So whenever we have vector space V and this function depend on vector space, we say that V along with this inner product is a this map is a inner product space. So we know several applications of examples and applications of inner product spaces, but we studied inner product spaces only for the finite dimensional inner product spaces. But in this course, we will discuss infinite dimensional inner product spaces. So let us start with the finite dimensional case. So V is Kn, where K is either set of real number or complex number, right? Then, yeah, so how to define an inner product here? So we know that in our notation we are using coordinates as K1, K2, Kn, and another function, so K dash 1, K dash 2, K dash n. So these are the two elements of Kn. Then inner product between these two vectors, inner product map. So this we defined as K1, K dash 1 conjugate plus so on. Last one is Kn, K dash n conjugate. In other words, it is summation j1 to n kj k dash j conjugate. So this is inner product, and yeah, so this we know verification is very easy, that this satisfies the properties of inner product. So another example is coming in terms of continuous functions. So let us recall one easy lemma from calculus. So if we have a function from closed interval 0, 1 to r, so we have a non-negative continuous function. We are taking closed interval 0, 1, but we can take in fact any closed interval a to b. This works there also. Yeah, so do you remember what is the proof? So this is said that if we have a non-negative continuous function over a closed interval and area under that function, the graph of the function is 0, then the function is identically 0 on that closed interval. Okay, so to prove this result, let us assume that f is not identically zero function on the closed interval. So it is not identically zero means we know that it is non-negative function. So if it is not zero everywhere, then that means at least one point is there such that the function is taking positive value there. So now we can use this as a positive number and we can use the continuity of the function at t naught. So what we'll do is we will assume epsilon in terms of this value. So that is half of this value. And since f is continuous, there exists delta greater than 0 such that, so by the definition of continuity at t naught we get t minus t naught less than delta. Whenever this is satisfied, then we get ft minus ft naught less than epsilon, but epsilon is essentially this number ft naught by 2. Yeah, so this gives us the value of ft is between ft naught minus ft naught by 2 and ft naught plus ft naught by 2. So that will give us ft belongs to ft naught by 2 to 3 times ft naught by 2, and ft naught is positive. So that means ft is greater than 0 for all t belongs to this positive integer. So if you know that if ft is positive over the positive length interval, then the integration over this side, yeah, so t belongs to what? T belongs to this interval. So this is a mistake. T should be in t naught minus delta to t naught plus delta. So now we take integration over this interval of ft function. Then since it is positive on this interval, this is greater than 0, and that will force that the integral of ft, which is bigger or the equals to this interval, which is positive, which is a contradiction. Yeah, so this is a contradiction because in the statement it is given that the integration of ft is 0. This contradiction coming from the assumption that f is not identically 0, so therefore f is identically 0. Okay, so this is the simple result from kind of calculus. Yeah, so here the criteria is very important that the function is continuous. If we relax this condition and if we assume that the function is Riemann integrable, then this result is not true. So here we cannot relax the hypothesis by assuming that f is Riemann integrable. We know that every continuous function over a closed interval is Riemann integrable, but there are functions which are Riemann integrable, they are not necessarily continuous functions. So therefore, this is a weaker condition than continuity. Yeah, so what is the example? So example is, and take a function which is discontinuous at a particular point. So take function which takes value 0, t is equals to half or 1 by 3, and takes value 1 or any number at t is equals to half. So other than half it is 0, at half it is taking one value or any positive number. Then using the theory of Riemann integration, so you can use partition and check that the integral Riemann integral of this function is 0, right? But this function is not identically 0 because f of half is non-zero. Right, so basically f is not identically 0. So you must be knowing all these example, but they are the standard example. So using on the space of continuous functions, also we can define the inner product. So if we take the set of continuous function over closed interval 0, 1, then we can define what is the inner product. Can you tell me? So you must be remembering this from linear algebra also, that the inner product is ft gt conjugate. Right, so this is a, we can easily verify that this function is an inner product on C01. So in future, whenever we will say C01, that means the set of continuous functions over the closed interval 0, 1. Okay, so now we know that every inner product space, that means vector space along with inner product, gives us and the induced norm. So norm is basically norm of x defined as square root of inner product x with x for every x in x. Right? We can check that this function satisfies all the properties of norm. So the example is on C01, we have just defined the inner product, so that gives us norm of f, which is square root of inner product f with f. So that is nothing but integration ft into ft conjugate dt, square root of that, and that is nothing but square root of integration mod ft square dt. This is the corresponding norm coming using this inner product. And then we know that every inner product space satisfies the Cauchy-Squarz inequality. So that is Cauchy-Squarz inequality is that the modulus of the inner product of x and y is less than equals to norm x times norm y. Where x and y are elements of x, elements of v. And every matrix space which is complete, we call complete matrix space. Similarly, every complete inner product space is called a Hilbert space. Right. So this is first definition. Second definition is every non-linear space which is complete is called a Banach space. So every inner product gives us norm, but converse is not true. Every norm doesn't need not be coming from the inner product. Right. So may not be every non-linear space may not be an inner product space in general. Yeah. So think about these, find examples. So basically, if you remember the inner product space, what is the use of inner product space? Why we studied that? Yeah, why we study in the product space? Yeah, Vibhav,
So compute lengths, angles, etc.
length we can find using norm also. Yeah, angle, that is correct. So angle we can find, right? So basically, orthogonality. We know that if two vectors has in a product zero, that means they are orthogonal. Yeah, angle also we can, any angle we can define using that cos theta formula in terms of in a product. But mainly we can define orthogonality, and we studied in school the Pythagoras theorem. So, so that is regarding right angle triangle. So basically, we can consider that in terms of vectors. So we would recall the Pythagoras theorem for inner product space. So if we have an inner product space, then and if x is orthogonal to y, so that means basically inner product of x and y is 0, then norm of x plus y square is equals to norm x square plus norm y square. So this is main property. If the norm is coming from the inner product, it must satisfy this result. So this is one of the tests that our vectors are the non-linear space is actually an inner product or not, that we can verify using this type of result. Okay, so we'll see example later on, but today we want to discuss a theorem which was which is known as Baire category theorem. So this is regarding the complete matrix spaces. Let X be a complete matrix space, and if we have a sequence of dense open sets, right, d1, d2, d and so on. If we have a sequence of dense open set, then the intersection of them open is important here. So that's countable number of, so intersection of countable number of dense open sets is also dense in X. For example, set of rational number is dense in R. The set of irrational numbers is dense in R, but their intersection is null set. So it is not dense in R. So, but this is not we are saying, because we are taking the open sets which are dense. So Q and R minus Q are so whether they are open set.
No, sir.
So why?
Sir, for Q is not open in R because we can found a neighborhood which contains for every epsilon greater than zero, we have there are
Yeah, yeah, it is
uncountable
open.
number of
It is not
irrational
open.
numbers.
Yes, yes. So irrational density theorem, right? And similarly, R minus Q is also not open. Uh, yeah, so I thought in the other way, Q is closed basically. Fine. Yeah, so that is correct that we cannot, it doesn't contradict this theorem. So let us try to prove this theorem. So proof is quite technical. First, we will show that the finite intersection is dense, and then we'll show that infinite intersection is dense. So we are taking the collection d1, d2, and so on. The dense open subsets of the metric space X. So if you take what is the definition of dense set? So we take any neighborhood. So neighborhood here means in metric space it is a open disk. So if we take any open disk around that point, that should intersect with the set if it is a dense. First we are using D1 is dense in X. So let us start with some point and disk around that point. So let X naught belongs to X and R naught is the radius of the disk. So since D1 is dense in X, D1 intersection this neighborhood is non-zero. So if you draw the diagram, so if we have the set, let us say this is D1, which is dense in the metric space X, and we are taking a point which is, so let us take some point X naught, and we take a neighborhood of radius R naught around X naught, then it intersects with D1. So since it intersects with D1, let us say that it intersects in the point X1. Right? So since this intersection is non-empty, therefore there exists X1 in X such that X1 belongs to open disk centered at around X naught, radius R naught, intersection D1. Fine. So now we know that this is open set, right? Open dense subset. This is also open. So intersection is also open, right? Intersection of open set is also open, and X1 is an element in the open set. If we take any element in the open set, we will get a neighborhood around that point which is contained in that open set. So since u x naught r naught intersection d1 is open, there exists some radius such that the disk around x1 and radius r1 is contained in this open set, right? So we will choose this r1. We shall choose r1 such that it satisfies certain property. So that property is that its closure of the second disk is contained in the first disk, right? So let us uh, so what we'll do, we will choose in the way that the closure of x1 r1 is contained in d1 intersection u x0 r0, right? So here what was there? Here we are saying this disk is contained here because it is open, but we shall choose r1 basically small enough. If you want, we can take this radius half of the what we are getting, and that small enough radius we can take so that this holds. So later on we'll fix this radius also, that this radius is less than equals to 1 upon n. Yeah, but as of now we are selecting r1. So proceeding in this way, similarly, so what we have got is we got a neighborhood around x1 of radius r1. So now since d2 is a dense in x, we get another radius so that u of x2 r2 is contained in d2 intersection u x1 r1. Yeah, so before that we get x2 in this set. So u x1 r1 is open set around x2, d2 is dense, so that means x2 is in d2 intersection the neighborhood because of the density of d2. So proceeding in this way, we get the points basically x1, x2, x3, xn. So by mathematical induction we get radius is r1, r2, rm, positive real numbers such that so inductively what we get u of xn rn at the nth stage, which is subset of dn intersection 1 less, so xn minus 1 rn minus 1 for every n is equals to 1 2 up to m. So this is what we get by the mathematical induction. So for 2 we have done first, and then we will do for 1 2 up to m, where m is a natural number. Note that xm belongs to this disk, right? So basically corresponding to xm, the radius is rm, and this set is contained in dn. And further, right, because each of these is contained in dn, and we are selecting the disk so that the new disk is contained in the old disk. So therefore disk we are getting smaller and smaller, so each disk is contained in each dn, and each dn before that, and moreover we get each xm is also belongs to ux naught r naught. So you can see x1 is in ux naught r naught. Now again the next disk will be inside this disk. So diagram I am not drawing, but we can see this easily, and therefore xm belongs to the finite intersection of dn, right, because it is in each dn intersection the disk. What does this mean? This means intersection of ux naught r naught, we started with that disk, right, that is open disk around x naught. That disk intersects with finite intersection of dn, so that will give us finite intersection of dn is dense in x. So we are taking infinite sequence of dense subsets, but first of all we have proved that its finite intersection is dense, and now we will prove that the infinite intersection is dense, right? So further, without loss of generality, we may assume that now that radius thing will come, so we can assume that the radius which we are choosing one by one, r1 r2 r3 rn, they are bounded by the sequence 1 upon n, and they satisfy this particular condition, that closure of xn rn, closure of uxn rn is subset of dn intersection uxn minus 1 rn minus 1. Right. So that is what I was saying earlier, that this second disk we are getting, we can choose its radius is small enough so that r1 is less than equals to 1, right, r2 will be less than equals to half, r3 will be less than equals to 1 by 3. That way we can select the disk, and they also satisfy this extra condition, because since we are choosing the small enough radius, so this is smaller than 1 upon n, but even we can take rn even smaller, so that they satisfy this property. The closed unit disk of the next disk is contained in the open unit disk. of the previous stage. So that will be for all n belongs to n. So now more or less we are done using this property, because now we can use that if epsilon greater than 0 is given, since we know that 1 upon n sequence converges to 0, we get some positive integer satisfying 2 upon n naught is less than epsilon. Alright, because now we want to use the completeness. So far we have not used that x is complete. X is a complete matrix space. So to use that x is complete matrix space, we are starting with epsilon, and using that epsilon we are getting a number n naught, so that 2 by n naught is less than epsilon. So basically we are using 1 upon n converges to 0, or you can say 2 upon n converges to 0 sequence. So for all n and m greater than equals to n naught, we get xn and xm both belongs to u xn naught rn naught, right? Because we observe at some stage that each xn belongs to the previous stage. So x1 belongs to this ball, to x naught r naught. Similarly, x2 belongs to u x1 r1 as well as u x naught r naught. So whenever we take m bigger than n naught, xm will be in uxn naught rn naught. Similarly, xm also belongs to uxn naught rn naught. Using this we get the distance of xn with xm. We want to show it is a Cauchy sequence. So this is less than equals to, we compare the distance with xn naught. So first we are using triangle inequality of the matrix, and then we know that distance of xn with xn naught is less than equals to rn naught. Similarly, distance of xm with xn naught is less than equals to rn naught, right? So this is basically 2 rn naught, and rn naught we know that rn is less than 1 upon n. So rn naught is less than equals to 1 upon n naught. So that we can use here, rn naught is less than equals to 1 upon n naught. So now we got that number 2 divided by n naught, which is this one, right? And that is less than epsilon. So n naught we are choosing such a way that 2 upon n naught is less than epsilon, and for this particular n naught we are getting this is less than epsilon. So therefore xn is a Cauchy sequence in the complete matrix space X. X is the given matrix space which is complete, that is given in the statement. X is a complete matrix space. So that is also important. This result fails if we are not assuming that this is a complete matrix space. So we know that if matrix space is complete, then every Cauchy sequence converges to some point in the set. Therefore, there exists x belongs to x such that the sequence xn converges to a particular x, because x is complete. So now for every fixed positive integer, the distance of xm with x capital N, which is less than equals to Rn, for every m greater than equals to n, right? Because we know that every point is contained in the next disk. So this holds. And in this, now what we can do is take m approaches to infinity. This is true for all m greater than equals to n. And then we take m tends to infinity. So what we get is, whenever m approaches to infinity, xm converges to x. So we get x with xn, which is less than equals to Rn. Right. So that means x belongs to the closure of the disk centered at xn with radius n. Right. So this means this, and so now we can use that closure property that we have assumed, special property, that if we take the closure of the disk, then closure of the disk is contained in dn intersection u xn minus 1 Rn minus 1. So here that closure thing is used because we are taking the limit. The limit is contained in not in the set but its closure. So that is contained in the dn intersection open ball of xn minus 1 Rn minus 1. And if we take this index, we know that each bigger disk is contained in xn naught, right? In this, each x1 R1 is contained in x naught R naught, x2 R2 is contained in x1 R1 ball, which is contained in x naught R naught ball. So that means it is contained in x naught R naught. So this is true for every natural number n, capital N, and that will give us x is element of these, so we can take in the intersection. Right, so this is basically this is subset of intersection dn. In fact, it is same. So we got a point which is in this intersection. So we started with any point x naught. We have taken disk around that point, and this disk, open disk, intersect with the intersection. It's capital N. So that means this intersection is dense in X. So we proved this result, and we proved that we know the Dn are dense subsets of X, open dense subsets of X, and we proved the intersection is dense in X. But we are not saying that the intersection is open. So do you know any example where the intersection, infinite intersection of open set is not open?
Intersection from n to infinity minus 1 by n to 1 by n open.
Yeah, so what is the intersection is 0, right?
Yes, sir.
Yeah, so this is the example. So all these sets are open, but the infinite intersection of open set is closed. All right, so therefore we in the topology definition we are taking arbitrary union and finite intersection of open sets. So finite intersection of open set is open, but that is not true for the infinite intersection. Okay, so one result we want to discuss next is regarding continuity in matrix spaces. So we know that if we have the matrix species, then we can define the continuity in matrix space the same way which we define in the usual R2 or real numbers. But in matrix space there is a special benefit that everything we can define in terms of sequence. So in matrix space we can define the closed set in terms of sequences, right? The closure we have defined in terms of sequences. We can define the compactness in terms of sequences. We can also define the continuity in terms of sequence. So let X and Y be matrix spaces. So a map from a map T from X to Y is continuous at the point X naught in X if and only if we have a sequential continuity. Sequential continuity means whenever xn is a sequence which approaches to x naught, t of xn will approach to t of x naught. So this condition is known as sequential continuity. So it is useful in calculus and real analysis. It's also useful in the study of matrix spaces. So let us prove this. The proof is very easy. So suppose we assume that t is continuous at x naught. So if t is continuous at x naught, and basically x naught is a point of x, x is a metric space. So yeah, so by the definition of continuity, so what is the definition of continuity? For every epsilon greater than 0, there exists beta greater than 0, so that whenever distance of xn with x naught less than delta, we have, yeah, in general, we have x with x naught less than delta implies distance of tx with tx naught is less than epsilon. Yeah, so if this is given, now we want to show that the sequential continuity. So sequential continuity means whenever xn converges to x naught, we get txn converges to tx naught. So from this definition star, sequential continuity is simple because since xn approaches to x naught, right? So therefore, for every epsilon greater than 0, there exists some positive number so that xn approaches to x naught for all n greater than. So this is coming because xn approaches to x naught, and whenever, yes, this we are doing for delta actually, so that we can use star. Now xn, distance of xn and x naught is less than delta, so whenever such happens we get this. So therefore using star we get the distance of t of xn with xn naught is less than x naught. Using the definition of continuity, since xn approaches to x naught, we are getting t of xn converges to t of x naught. So this is also true for all n greater than capital N. Therefore, the sequence txn, which is a sequence in y, approaches to tx naught, and conversely, so conversely, suppose the sequential continuity is given. So that means xn approaches to x naught implies txn converges to tx naught. That is given. So we want to show that the property star holds, right? So basically, we want to show T is continuous with respect to the original definition of continuity in the metric space. So suppose star is does not hold. If star does not hold, means we need to find the negation of this statement. So to find negation of this statement, we know that we need to replace for all by there exist, and there exist by for all, and the property will fail. So property will fail means distance of x with x naught is less than delta, but we will not get the distance of tx and tx naught less than epsilon. So that means we'll get distance of tx and tx naught greater than equals to epsilon. So let us write down the negation. So if this does not hold, we get there exists positive number such that for every delta greater than 0, so that for some point x with x naught less than delta, property fails. So property fails means distance of tx and tx naught is not less than equals to epsilon. That means it is greater than equals to epsilon. This holds for some x depending on epsilon. So now, since this is holding for every delta, we choose delta to be 1 by n. So in that case, for every natural number, we get delta. So we get corresponding x. So we have for each n we have xn such that distance of xn with x naught is less than delta. So delta is 1 upon n, but distance of txn with tx naught is greater than equals to epsilon. So if we have such a sequence xn coming from this delta, right, xn is a sequence now. So then what we get is using this property as n tends to infinity, xn approaches to x naught. But on the other hand, we have this inequality. So if we take n tends to infinity, txn will never approach to tx naught because epsilon is positive. So this is a contradiction, and this is coming from the assumption that star does not hold, so therefore star holds, and hence we get a theorem. So this is just a sequential continuity, which is uh, the characterization of continuity in the matrix space. Okay, so let me stop here today. So in the next lecture, we'll discuss some examples of complete matrix spaces. So Rn and continuous function on closed interval AB with the supremum norm, they are complete matrix space. So that we'll prove in the next lecture on Monday.